Okay, so the warm-up was trying to get you to distinguish between your ionic and covalent stuff. So everything up to this point, and don't forget how to do the formulas and do the naming. Make sure if you are already behind on that, you're either looking at the videos and trying to catch yourself up, or you should be making time to come in to get tutored. Okay, but as far as the warm-up went, for any of the formulas, what were you asking yourself? If it had a what? If it had a non-metal and a metal. So really what we were looking for is if it had a metal, we were automatically on ionic, right? And then if it did not, then we were saying it was covalent. And then you had your properties from yesterday that we were going over, which would be the high melting point. You had it's soluble, and you knew that it was an electrolyte. And then there were a few other things that showed up. So I will just kind of circle the ones that are ionic, and I will cross out the ones that are covalent. Okay? So we're just going to go through the whole page real quick. So CH4, methane. Covalent. Okay? So high boiling points. This is ionic. Okay? O3. Covalent. How many, or I'm sorry, many are insoluble in water. This one's covalent. Okay, if you look, when you guys get your lab back, you'll study those lists. All right. Insoluble means does not dissolve. Insoluble means does not dissolve. Okay. All right. H2. Covalent. Magnesium oxide. Known as molecular compounds. Covalent, good. Sodium bromide. That's ionic. Okay, organic compounds such as carbohydrates, lipids, proteins, nucleic acids. This is covalent. Okay. Hydrogen chloride, yeah, sorry. Covalent. Sorry, I was thinking back to this. So last year in bio, you guys saw a lot of phosphorus and nitrogen and oxygen and carbon. That's kind of what that one was based off of, just so you know, okay? All right, calcium chloride. Ionic. Nonmetals bonded to each other. Covalent. Nitrogen trihydride or ammonia. This is covalent. Okay. Sodium chloride. Potassium sulfide. Potassium oxide. High melting point. Potassium iodide. Potassium chloride. That's a lot, huh? Soluble in water. Good. Potassium trichloride. What? This one's covalent. Potassium. I'm so sorry. Brain is foggy. Phosphorus trichloride. That explains why you guys answered what you did. Sorry, my bad. All right. Potassium bromide. Good. CH3CH2OH. That is covalent. Good. All right. Low boiling point. Covalent. A metal bonded to a non-metal. Good. Sorry. Dihydrogen monoxide. Covalent. Sodium fluoride. Low melting point. Carbon dioxide. Good. Okay. So I'll just kind of zoom out so you can double check your answers, the ones that were circled. These are all the, oh, sorry, not that one. These were the ones that you colored, huh? You have to name them and write formulas.
As in like the names that we did, like
Mm-hmm. Okay, so basically, just a reminder of what we kind of went over with this yesterday was we talked about how your electronegativity values, which are how much these things are pulling on electrons, Okay, I told you it was very specific to when they are bonding. These differences between them, so if one is pulling harder than another one, that's how we get our different types of bonds between the two atoms. Okay, so you should have just done simple subtraction for this whole column, and then you should have applied it to what was on the spectrum over here on number 4. Okay, to figure out if they were polar covalent or non-polar covalent. We're going to talk though about what those actually mean now. Okay, so for the electronegativity worksheet, the right-hand side of your page, we're going to fill out those. So how are ionic and covalent bonds different? So this should just be review. Let's talk more about what's happening with the electrons.
Covalent, they're like working together.
Okay, so electrons are shared for covalent. What are they for ionic?
I don't remember if they replace each other.
They're transferred. Okay. Now the next question is asking, how does a polar covalent bond differ from a non-polar covalent bond? Okay, and so basically, a polar covalent bond, let's just give an example for your page, would be like something between hydrogen and fluorine. Okay, so between hydrogen and fluorine, so we're going to, what I want you guys to do is kind of make like a little lopsided blob like that. Okay? Make a little lopsided blob. So fluorine gets the bigger end of the blob. Hydrogen gets a smaller end. Okay? So what's happening here, what this picture is showing you is obviously an imbalance, some sort of an imbalance, okay? But what you guys could tell me is who's pulling on the electrons more? Fluorine, because its electronegativity value is the highest, right? So what you can kind of imagine is all of these electrons that these things are sharing, all the electrons are kind of leaning towards fluorine, okay? So fluorine has a very dense electron side, and so all these electrons are just kind of leaning towards it. So if they are all leaning towards it, what does that tell you about this side in terms of being positive or negative? If all the electrons are leaning on that side, it's more negative, right? So what we call it is not a negative side, it is a partially negative side. So you'll see these symbols. So I do want you to draw that. Kind of looks like a music note. It's a lowercase delta. That's a Greek symbol. Okay? And then the hydrogen side, who does not have very many electrons, because they're all leaning the other way, is a partially positive side. The other symbol I'd like you to add to your little picture here is an arrow pointing to where those electrons lean. So it points to the more negative end. And so then we put a little thing to indicate positive on the other end. That's not really what that's for, but that's the easy way to remember it. Okay? So those are the two different ways that we would see this symbol. But what it is that hydrogen isn't tossing its electron to fluorine, okay? It's still sharing. They are still sharing those electrons, meaning neither of them are taking ownership of the other one's electrons. They're sharing them, right? But they can kind of lean to one side or the other, whereas a non-polar covalent bond could be something, we can go ahead and just do, we could do 2 fluorines, like that. And we'll just give it one big circle. That's, I know mine looks lopsided, but it's evenly distributed. There's not a bigger end and a smaller end, okay? Meaning these electrons are pretty equally shared, okay? So this one doesn't have this partially negative, partially positive side. Nothing's leaning, all right? But it has to do with having that high electron density in this polar covalent bond, okay? So looking at these images, can you kind of distinguish the difference between a polar versus non-polar without me telling you more details so far? So polar if you could say it in your own words, what would be polar?
There's positive and a positive and a negative side.
Partially positive and negative. So maybe let's stay away from that one. If you could say it in one word, what would you say about that picture? Huh? For polar?
Oh wait, no.
Oh.
Not equal.
Unbalanced, not equal. I would say lopsided, right? Okay? It's the one where it's not balanced. Like truly not balanced, okay? Your non-polar means that you are it's pretty uniform throughout, okay? So this is shared equally. So I do want you to write that here, and maybe that'll help out a little bit. Okay? But the difference is that polar ones are not shared equally. Non-polar are shared equally. Okay? And we're talking about the electrons specifically. Okay? All right. So your electronegativity values help us come up with those two pictures because electronegativity is how much an element is pulling on electrons. Okay, so therefore, a bigger difference will be more ionic, or the idea of it transferring. A medium difference is going to be that polar covalent, and a small difference is going to be that non-polar covalent. Okay? So if electronegativity is just how much they're pulling, we can put it into those three categories. Okay? So think of tug-of-war games, right? So one side has to pull harder than the other, right? And that's exactly what's going on here. It's the same idea. All right. So one thing I do need to make sure you have updated is I might be changing the values for y'all. I don't know which ones I gave you guys yesterday, but I would like you guys to use these now. So use a 0.4 on this one, a 1.7 on the second one, and we don't even worry about that last one because it doesn't really make sense to put a limit there. Okay? And please remember what I said yesterday. These are very general numbers. Like they are not, it's not clean cut. Okay? It's not black and white. It is big gray right there. Okay? So you might have something that's 0.5, but it's more on the non-polar side than polar side. So things that we might look at instead is what types of elements are involved. We can treat it more like comparison. So if you know you have a metal and a non-metal, then it obviously goes in the ionic side. If it's not a metal and a non-metal, it should be more on the polar, covalent side, okay? So just treat it like a spectrum. It's a continuous spectrum. There's not a clear line on any of these, okay? It's just general areas. So those are what I want you to use, though, for future, like any calculations, I want you to use that spectrum. So the 0.4, 1.7, okay? All right. So number 5 and 6 are just reviews from the last chapter. So real quick, electronegativity, does it increase or decrease as you move across the period? Increases. Okay. Does anybody remember why? Inside. What's on the inside? It's the number of protons. That's what I was trying to tell you. Inside, not outside.
I said more protons.
No, you said more electrons.
No, I said protons.
Oh,
Or
okay.
I said electrons at first.
Okay, all right, well, that's the part that I heard. Sorry. Okay, how about moving down a group?
Less. It's less.
Right, so it decreases. Why? More energy levels. We gotta keep going. Sorry. Okay. All right, and then you guys can handle number 6 on your own. That's just talking about you don't need those electronegativity values. You just need to know the trend. You just need to know the trend, and then you can kind of start deciding, okay, if they're really close to each other, they probably have very similar electronegativity values, then you can kind of figure out what the bonding is. Okay? So we're going to kind of leave that the way it is. Make sure tonight you check this with the answer key online. Okay? So basically that page that you guys got back from me yesterday, that one is going to be posted. This will be posted. So everything up to this point will be posted so that you guys can actually check your answers on things. So that means if you have any late work, you need to turn in by the end of the today. Okay? All right. So moving on, go ahead and go to a clean page in your journal. We have one last thing to squeeze in. Okay. And if you'd like to save yourself a spot for the lab page to get back to you, you can do that. You just need one page. Or you can just wait and put the page at the end of this chapter. And that's fine. But in your lab journal, we're going to worry now about drawing covalent bonds, right? So covalent drawings. So these are Lewis structures. So this is with the covalent bonds, all right? So our molecular compounds or molecules, as opposed to what we did for ionic. Remember, ionic was the one where we showed the transfer, and then you ended with little brackets, and then that was your answer, right? You guys had to show me the whole electron transfer. So this is not that. That is how we deal with metals bonding with a nonmetal, okay? So Lewis structures is going to be when we have two nonmetals, and we now have to form these little funny shapes. So this chapter, we're not going to worry about the funny shapes. We'll save that for after this next test coming up. But you are going to be responsible for drawing them. Some people have learned in the past how to make these, and usually the teachers describe it as connecting the dots. I don't want you connecting dots. Okay, so if that is you, just please open your mind to the new way. I need you to do it my way because I promise there's a reason I make you guys do it. Okay? So what we're going to do is, it's called needed, available, shared. Okay? Or NAS. Okay? So, and we'll run through what each of these mean. We're not going to spend too much time writing all these details because honestly, I could sit here and talk at you, but it's not going to make sense until we start doing a bunch of examples. So we want more examples so that homework is easier tonight, okay? So N stands for needed. Okay? Now needed is like the goal. Okay? Meaning most of our elements up on that periodic table, what is their ultimate goal for valence electrons? To have 8, right? So for this, your answer, if I'm ever asking, okay, how many are needed, it's 8. It is 8 for each element. Unless, I know, dun dun dun. Unless you have hydrogen. Hydrogen only needs 2. He's on the 1s sublevel, so he can only fit 2. Okay? Beryllium, you guys don't use this one too often, but that one's a 4. And boron is a 6. Now, it might bother some of you guys that we're dealing with beryllium and boron. Aluminum's going to bother you too. You will be drawing a couple covalent compounds with those. Once again, it's that shade of gray there, right? Where it's kind of that blurred line between ionic and polar covalent stuff, okay? So just know that if those pop up on any of the questions, use the 2, 4, 6. Otherwise, no matter what, you guys are telling me 8, okay? All right. A stands for available. I probably should not have wrote this in purple. That's okay. Okay, so available. What do you guys think available is talking about?
How many are there?
Right, so how many are there? So valence electrons. It's going to be valence electrons, okay? And most of you guys have gotten pretty comfortable with finding your valence electrons. You're going to pay attention to what group they're in, what column they're in, okay, to get your little valence electrons there. All right, if you notice, it is just a subtraction going on to figure out shared. So this is talking about how many these atoms that are getting bonded together in a molecule, how many electrons are being shared. They get shared in a what? Bond. Yeah. Okay, so they get shared in a bond. So what we do is we take that number, and every bond has 2 electrons. So we're going to divide it by 2 to figure out the number of bonds. This right here is why I make you guys do a NAS, because it's going to help you find your double and triple bonds when it doesn't seem overly obvious. Okay? So, the only last thing that I want you to do, oh, let's write 2 side notes real quick. All right, so next to this bonds, I want you to say 1 bond is equal to 2 electrons. Now, that might be common sense for some, but some of you guys are going to need that little reminder in a second. Okay, 1 bond only has 2 electrons. Okay, we're talking about like the actual thing that is connecting them. It's the fact that those orbitals are overlapping each other, so 2 things are getting shared, 2 electrons. All right. The only other thing I want you to add to this little list is put a bunch of stars next to available, because that is the most important number on here. We're going to have to come back to the available at the very end of every single drawing to make sure that that is how many you have. This is also how we deal with the weirdo ones where we have expanded octets, but y'all don't have to worry about that yet. So I'm just going to kind of push this off to the side. So let's start with the first example. Let's go simple. Let's just start with dioxide or diatomic oxygen. Okay. So for this one, we have needed, available, shared. What my students in the past have done is they'll put the actual elements that are listed, they'll just list them all out across, and then that way they know what numbers go below them. All right, so this is just an oxygen and an oxygen. You see that? So for needed, how many does the first oxygen need? 8. Good. How many does the second oxygen need? 8. Add them together. What do we get? 16. So remember, for the needed line, usually it's 8, unless you're dealing with one of those exceptions. That's where those numbers came from. All right, available. So available is the valence electrons. Each of your oxygens have how many valence electrons? 6. They're in group 16. So you have 6 for this one. We have 6 available for that one. So total, we have 12. What are we doing with those 2 numbers? We're subtracting them to get 4 electrons that need to get shared. So we divide it by 2 in order to find 2 bonds. So this right here is going to show you a double bond automatically. Okay? So now that we have this information ready to go, we're just going to draw our 2 oxygens next to each other. We're going to give it a double bond, meaning 2 lines. And now we have to fill in the rest of the electrons. Because, remember, what is the most important number?
6.
12. Remember, the one that we drew all the stars next to. All right. So we're gonna go, and we have to make sure we show all those, okay? So each of the bonds has how many electrons? 2. So we have 2, 4, 6, 8, 10, 12. Okay? And now you're done. Questions? Okay, so we have, let's do CH4, because that works with one of the exception ones, okay? So methane. All right, so for needed, available, shared. Needed, how many does the, sorry, this is what they would do. They would just list them all out like that so they can write their numbers below it. So carbon needs how many? 8. Hydrogen? 2. This hydrogen? 2, 2, 2. Okay, so we have 2, 4, 6, 8. 8 plus 8 is what?
16.
Good. Okay, available. Carbon has how many available? 4. 4 was right. Each hydrogen has how many?
1.
Okay. So that would give us 8 total. So 16 minus 8 is 8. Divided by 2 is 4. Now this one is a really obvious one to draw, and it's probably going to frustrate some of y'all that we just did that whole math thing for it. But you would put carbon in the middle, okay? Whenever, and that's a rule. If you ever have carbon available, put them in the middle. Carbon likes to be in the middle. He has the most bonding sites available, okay? So we put carbon in the middle, and we need to have 4 bonds going around carbon.
Oh.
And now we're going to add in the other letters to it. Okay? But our most important number on here is this 8. We got to make sure that there are 8 electrons in this picture. Are there 8 electrons in this picture? Yes. 1, 2, 3, 4, 5, 6, 7, 8. Okay? You see that? Okay. Let's do another example. Are you ready for another one? Carbon dioxide. Do it. Carbon dioxide. So if you're working through NAS, you would put carbon, oxygen, oxygen, and start doing your little calculation thing there. So give it a try, and then we'll check it together. All right, so for the needed line, how many did the carbon need? 8, and each oxygen? 8 and 8. Okay, so we had 8 times 3, which is like 24-ish. Yeah. All right, available carbon has 4, oxygen 6, this oxygen was 6, so we had 16. So subtracting those, we get 8 divided by 2 tells us 4 bonds. So, just like the last one, I told you carbon goes in the middle. So you put carbon here, and you have to have 4 bonds coming out of it. But how many other things are actually getting attached to it? Only 2, right? We only have an oxygen here and an oxygen here. So what do we do?
Dots.
Double bonds. Yeah, good. This is why NAS is nice, because it will tell you on those little instances when you have a double bond or a triple bond. Okay? All right, but we're not done yet. We got to go back to the 16. Okay? And so we get 1, 2, 3, 4, 5, 6, 7, 8. So I'm at 8 so far. We need to have 16. So 10, 12, 14, 16. And that's what carbon dioxide looks like. Yes.